In this video, I'm going to go over the use of protecting groups on alcohols. So hydroxyl groups are reactive, as we've seen from the different videos so far with the reactions that they'll undergo. Sometimes we want to do a reaction without reacting the hydroxyl group. In these cases, we're going to need to use a protecting group. And a specific example, and one that's very common with protecting groups, is going to be with Grignard reactions, because any Grignard reaction with either a hydroxyl group on the Grignard or the substrate requires a protecting group. Alright, so let's say we want to do the following reaction. We've got a ketone, and we want to react it with that Grignard reagent to give us a diol, right? 2 alcohols on it. We want to do that reaction. The problem is we have a hydroxyl group on a Grignard, and that will never form because when you add the magnesium in, all it's going to do is just deprotonate the hydroxyl group. You're never going to get your Grignard. Right? And then even if you do get that Grignard, now you have an O- also on it, and that could react as a nucleophile instead, so it just would not work. So what we have to do is install a protecting group before forming the Grignard. Okay, so how we do that is we're going to use one of the more common protecting groups, and that is trimethyl silyl chloride. The structure of it looks as follows. We've got silicon, 3 methyl groups, and a chloride. I'll just throw in the methyls here to make sure we know that they're methyls. Okay. So how this installs onto the hydroxyl group is silicons have a larger electron cloud, and thus they have longer bonds than a carbon does. So that means even though this silicon has 3 methyl groups bonded to it, so it's tertiary, it can undergo an SN2 reaction, whereas if it was a carbon, it couldn't because it was a tertiary substrate. So I've got my Grignard, or not Grignard yet, what's going to become the Grignard. I react this in an SN2 mechanism. Chloride kicks off. We're also going to have deprotonation. Right, I'm not going to draw the separate step for deprotonation, but you would just have the chloride deprotonate it, or a different base you might use to deprotonate it. And you'll end up with your protecting group now. You can also write this, right? This is the same thing. It's equivalent to OTMS. It's kind of like if you've used tosyl chloride before to make a hydroxyl group a better leaving group, you write that OTS, right? Same thing, OTMS is the abbreviation for this. Okay, so that is how we've installed our protecting group. Now we can turn this into a Grignard. So the synthesis, so we've got OTMS. All I do is I add in magnesium metal to install the magnesium on. So the magnesium's on. Next, I react first with my ketone, and then once it's reacted with the ketone, I can add in water to protonate the methoxy group. Right, but I don't add in water until I know that this reaction has happened. So then this leaves me now not an OH yet, because we still have our protecting group on there. So I've gotten one of the alcohols from the ketone, and then I just have to get this protecting group off now. So to get it off, I can use either H3O plus or F minus. And a common source of F minus is going to be TBAF. Right, that's the abbreviation for it. It's a nitrogen compound that is a cation, and then it has a fluoride anion in it. So if I use H3O plus or F minus, I'll remove the protecting group, and I get the final product that I want to get. So that is how you're able to use a Grignard reagent that has a hydroxyl group on it, or how you can use a Grignard to attack a substrate that has a hydroxyl group. You just have to protect the OH group using a protecting group, the most common of which is the trimethyl silyl chloride.